Hello, my name is Rohan-Paul and very welcome to my computer vision and deep learning YouTube channel. Let's get started. In this video, we will learn basic quantization technique in PyTorch, and the goal is faster model training and possibly better accuracy. First, let's just quickly understand why quantization is required at all. So, neural networks are implemented as computational graphs, and their computations often use 32-bit or in some cases 64-bit floating point numbers. However, we can enable our computations to use lower precision numbers and still achieve comparable results by applying quantization. So quantization refers to techniques for computing and accessing memory with lower precision data. These techniques can decrease model size, reduce memory bandwidth, and perform faster inference due to savings in memory and faster computing with int8 arithmetic. And now I will see an implementation in an actual code. So here I'm using PyTorch imports, all the regular ones, and then I will have a simple network build for my this network that you see currently. This is LeNet 5. So initially I have at the input end of the network 32 by 32 size image, and then it goes through a convolution and subsampling layer, then another convolution, another subsampling, and then I have a fully connected layer. And finally, from the network, the final output is a vector of 10 different classes. So this network architecture is implemented for a multi-class classification problem, and here is the code for this network. So I have one conf, another conf, then one FC layer, FC2 layer, and FC3 layer. I mean, for the simplicity for this particular video, I have not included the max pooling layer or the subsampling layer over here because I have a separate detailed video on implementation of LeNet 5. Here the purpose is to see how my quantization is affecting my training time, my model size, etc. So first thing is, after I have this class defined, I just want to check what is the current value of the parameters here, whether they are float 32, 64, 16, or whatever. So for that I'm just printing my f32. Let's actually run this cell. All right, and now I'm just printing my model. All right, it just printed the various layers it has, and then let's see what's the by default what is these parameter it has taken. So for that I have to run this cell. What I'm doing in this cell, it's just I'm printing all the named parameters. So I'll be for n and p, and then I will be I'll be printing the names and also the d type of p of the parameters. And from this I got the d type as float 32. So I can see that by default all computations and memory are implemented as float 32. And yeah, so now I am going to convert this default float 32 to float 16 with quantization. So basically I'm going to reduce the model to half precision in a single line of code. And the method I'm going to use is called half actually, and using half is often a quick and easy way to quantize your model. It's worth a try to see if the performance is adequate for your use case as a starter. So this is my code. Let's zoom in a little bit. Yeah, so I'm just taking FP32 model that was defined earlier and dot half. That's all you have to do. And now I'm printing again. And now I see all my parameters has been converted to float 16. And yeah, so that's sometime is the very first step. And I mean, in my cases, I pretty much keep my default parameters to f16, float 16, because it pretty much reduces my overall execution time by half and model size by half. So this was very simple and easy way to quantize my model, but in many cases, in most of the real cases indeed, you don't want every layer or every computation to be quantized in the same way, and also we may need to quantize beyond the float 16 type. We may need to go even further down. So for all those advanced cases, PyTorch provides three more methods to do that, which are dynamic quantization, post-training static quantization, and quantization error training. Now, dynamic quantization is used when throughput is limited by compute or memory bandwidth for weights. This is often true for LSTM, RNN, or transformer network. And static quantization is used when throughput is limited by memory bandwidth for activation and often applies for convolution neural network. And the final one, the QAT, is used when accuracy requirements cannot be achieved by static quantization. And also a good point to remember here that a small portion of the network, in particular portions of the softmax operation, must remain in float 32. This is because the sum of a large number of small values, that is logits, can be a source of accumulated error. So better to keep the softmax operation at float 32. So now with these three, let's just see quick example of these three. So for dynamic quantization, I am going to use the same model that we had earlier, which is my model named fp32 underscore model. That's what we had from this LeNet 5, fp32 underscore model. And for dynamic quantization, all I have to do is this simple code: import torch.quantization, then quantized model will be torch.quantization.quantized dynamic, and then to that pass the first argument as a model. Then specify the layers where you want to apply this dynamic quantization, and then dtype is where you define whatever the reduction in sizes you want in terms of the parameter number. So here I want int 8, so you have to mention torch.qint8, and then just run this. Let's run this cell and then also print the model, and then I'm printing the model. All right, so that's the same model. Now it is dynamically quantized, and let's check the linear layer if it is saying something. Yes, so my in features and out features, this is my linear layer, and dtype is torch.qint8. So this is an important thing to check after you do your dynamic quantization, that it really got implemented in your model layers. All right, now that was dynamic quantization. Now quickly compare my model size between fp32 and int8. And so for this, I just quickly wrote a quick function here to print the size of a model. So basically in this function, all I'm doing is I'm doing torch.save, that is saving the model with its state dict, which will have all the model weights, parameters, and all related relevant stuff, and saving the model as temp.p, and then I'm getting the size of this temp.p by ways.path.getSize temp.p, simple. And finally I'm just removing the temp.p and return size. That's what I need, and I am going to invoke this function for both my fp32 model and quantized model, that is the one that we just did in the previous step, this one. So let's just run this cell. F stands for my original fp32 model, Q for the quantized model. Run this cell, and I got the model size as the 32 is 126 KB and this one is 70 KB. It's like what you are seeing right now, it's like 50% reduction. That's because this LeNet 5, the one that I built, it's super simple. There is no deep layer, and the input to the model is also super simple, a single tensor. But for any real model, you will see for when you are moving from fp32 to int8, what we did here, you will see almost a 75% reduction in your model size. All right, now that was quantization, dynamic quantization, and now we will see a quick example code of static quantization. First, I'm reading from the official documentation of post-training static quantization. So it says that post-training static quantization involves not just converting the weights from float to int as in dynamic quantization, but also performing the additional step of first feeding batches of data through the network and computing the resulting distributions of the different activations. Especially this is done by inserting observer modules at different points that record these data. Let's quickly see a signature of these code for static quantization. And this is so our model was Linet 5, so I'm just creating a variable here, static quant model, and then you have to bring in the qconfig of quantization. Here you will define that. So here I'm just using static quant model.qconfig equal to torch.quantization.getDefault qconfig and fbgem. I will come to the point of what this means in a second. First, just completely check what I'm doing next, and then I'm doing a preparation. That is what is done with torch.quantization.prepare, and then converting it with torch.quantization.convert static quant model in place true. So this line get default qconfig, and then I'm passing fbgem. What it does is it quantizes weights on a per channel basis and uses a histogram observer that collects a histogram of activations and then picks quantization parameters in an optimal manner. Now, if you run this cell, let's see the output, then it will be a little bit more clear. All right, so this is my output. And what I have here is that it just printed all the layers and all the input shapes and things like that, the normal expectation. And then this is important, q scheme equal to torch.perChannel affine. This is for my fully connected layer 1. Similarly for fc2 and fc3, that is the next two fully connected layer as well, I have qs scheme equal to torch.perChannel affine and torch.perChannel affine. Now, talking about these torch.perChannel affine, let's quickly see what PyTorch says about that. So I am in pytorch.org blog. So they say that there are two quantization scheme. One is per tensor and then per channel. So quantization parameters can be calculated for the layer's entire weight tensor as a whole or separately for each channel. So under so what we just saw, that is per channel affine. So under these schemes, the separate clipping range is applied per channel, but under the per tensor scheme we can see the same clipping is applied for the entire tensor, and that's what it says, that in per tensor the same clipping range is applied to all channels in a layer, and but for the per channel it's separate. And then when we saw the definition of post-training static quantization in the official documentation, what it says is that this is done by inserting observer module at different points that record this data. Now in my code, back in my VS Code, where is that observer module? That is being taken care of by this line, torch.quantization.prepare. So this line will attach observers to the model. This will calibrate the training data. Calibration helps in computing the distribution of different activations. These distributions are then used to determine how activation should be quantized at inference time. But important thing to note here is this additional step allows us to pass quantized values between operations instead of converting these values to floats and then back to ints between every operation, resulting in a significant speed up. So basically this type of adding observer and static quantization allows us to pass quantized values between operations without converting back and forth between floats and ints in memory, and which is what helps us to in a significant improvement in the speed up of my training. And then finally the third kind of quantization, which is QAT, quantization hour training. So under QAT, it typically results in the best accuracy. Float values are rounded to the int 8 equivalent, but the computations are still done in floating point. That is, weight adjustments are made hour that they will be quantized during training. And this is my simple implementation of a boilerplate kind of code for my QAT layer. So I am just making use of the same model, Linet 5, then QAT model, then defining a qconfig, with the same FBGEMM, and then I am just passing these my original QAT model to torch.quantization.prepare QAT and QAT model, and let's run this cell. All right, so that was my QAT. And now I just want to show another example for the difference in model size between using quantization and not using quantization. But this time I'll be using a pre-trained model from Torch Vision, and the model I'll be using is MobileNet V2, and the code is this. So I'm just importing Torch Vision and then bringing in my model, MobileNet V2. So I have two model defined. One is with quantize equal to true, and another is I'm not passing these argument. That means quantization is false. And so the two models are model quant and model no quant. And now a very simple function just to do a torch.save of the state dict of the model, and the name will be demo.pt. And then I am just going to print these demo.pt size between these two models. Actually, I don't need this here. So then I'm just invoking this function to get the size of these two models. Let's see the size difference, if any. Yeah, you see, it's a really substantial size difference, because previously when I was checking the size difference with Lenet 5, I could not see such a substantial difference, because there my neural network was very simple, the depth was very low, and so that was the reason I did not see much of a substantial difference. The difference was, I think, 50% or so. But here I see such a huge difference. For quant model, I have only 3.63 MB of the model size, and it is 14.26 without the quantization. So that's the kind of benefit you get with quantization. And lastly, just create some quantized tensor to check that how they look like. So first I'm going to create a normal PyTorch tensor with this little code, t equal to torch.rand n, and let's print it. Yeah, so it's a vector, this list, which is my original tensor. And now first I'm going to convert this to a quantized per tensor. That's my code, torch.quantize per tensor. To it I pass this t, and we also have to mention the scale, the 0 point, and d type. And d type is the kind of d type I want. So here I want qint8 and run this cell. Alright, so that's my quantized tensor, and the d type is now torch.qint. Quantization scheme is torch.per tensor affine, because that's what we chose with this function, per tensor. And now I am also going to create a quantize per channel. For that, first I am going to create a new tensor. This will be a three-dimensional tensor. Let's create a float tensor named torch.rand1 223. Print it. Float tensor. Yeah, so that's my three-dimensional tensor. And now I have to define, before using torch.quantize per channel, I have to define scale, d-type, 0 point, and channel axis. And the difference this time is that for quantize per channel, my scale and my 0 point need to be a tensor. It cannot be a scalar like this. So let's just define those variable. All right, that's my scales. Scales is a torch.tensor, and just 1e minus 1, 1e minus 2, 1e minus 3. All right. D type is let's keep it at qint32. 0 point is again a tensor. Channel axis is 2, and now I can create quantized per channel. Alright, that's my code, torch.quantize per channel, and also print this variable q quantize per channel. Oops, what happened? Okay, I did not run this cell. Yep, so now it is converted to quantize per channel, and that's my resulting tensor. D type is torch.qint32, and the scheme now is torch.per-channel affine. And that pretty much wraps up this video, and over the coming days I will do many such videos on common techniques and tips of PyTorch while doing deep learning projects. So do subscribe and smash the like button. Thank you for watching. See you in the next one.